So the shortcuts continue. But today we're going to say, what if the function has a radical? Now, we actually did this one a while back using the definition. We had used the conjugate, and it got kind of weird. And so we're going to try and actually use a shortcut. But the funny thing is you already know the shortcut for this one. But this doesn't look anything like what we did the first day. So how can we possibly work with this to find the derivative? Well, what you're going to find is rewriting the original can very often be very helpful. We even dealt with negative exponents already, right? That's one thing that we've done. What's something else we can do? How could we rewrite the square root of x so let's just say x to some power? X to the 1/2 power. Very good. Okay. So it's x, if you remember, it's 1, and understood 2 is out there, right? So it's 1/2 power. So now we can go ahead and just use the power rule that we already know. Because now there's just a 1 out here, so you take the 1/2 times the 1, which is 1/2, and then x. Now here's where you have to be careful. You have to go down a power. -1/2. Very good. So now we got to kind of clean this up a little bit. So this 1 right there definitely wants to stay in the numerator. This 2 is most definitely in the denominator, correct? Where is this technically right now, based on the way I wrote it? Is that in the numerator or denominator right now? Technically it's in the numerator right now, but is it happy with being there? No. All right, so what we're going to do is the 1's fine, the 2's fine. That x is not all that fine because it has that negative exponent. And so you could write it like this, or to make it look like what we had the other day. Yeah, and let's face it, it took us way longer the other day using the definition to get the exact same answer. Now remember, this is the derivative, which is a general formula for finding the instantaneous rate of change at any particular point, or the slope of that tangent line at any particular point. That's actually on the graph. There you go. So can we use the same idea for this one?
Yes.
Okay, I heard one yes and one no. But the yes was way more emphatic. So as it is right now, we cannot. We have to rewrite it. So 1/2 times x to the negative 2/3. Okay. Nope, that is 1/2 times the cube root of x squared. Yep. It does kind of look like 2 to the 3rd, though, doesn't it? Hopefully that's clarified for those listening to the recording. All right. So now, that's just rewriting it. Now, let's worry about the derivative. So the 1/2 just kind of hanging out in front. Just hanging out, and then here's our exponent. So we have to take negative 2/3 times positive 1/2, which is a negative result. And it's a negative 1/3, right? And then x, and here's a lot of times where problems can happen. I have to take negative 2/3 and actually go down a power. Negative 5/3, very good. Because I really go down 3/3, right? And once again, we got to clean it up just a little bit. So we got to figure out what's in the numerator, what's in the denominator. Normally, I like to keep the negatives in the numerator, so we'll just do -1 over. The 3's happy with being down there. And really, right now, this x to the negative 5/3 is in the numerator, technically. So we would put it down here. X to the 5/3. Okay. So -1 over. If we were to write it back in radical form, and we could actually do more than what we're going to do here, but it'd be the 3rd root of x to the 5th. You realize some of these x's could actually get out if we wanted to clean that up, right? Everybody clear on that? That I could write it, just to make sure, I could write it as the cube root of x to the 3rd times the cube root of x squared. I hope we agree that that's the same thing as what's written over there, right? I would write it like that because this x gets out, is why you would write it. So it's -1 over 3x times the cube root of x squared. The only reason I'm really showing you this is in case your book writes it kind of different and you're like, wait a minute, that's not what I got. Okay, then you can realize sometimes, remember, if the exponent on the inside is greater than the root, some of them can get out. Okay. Everybody clear on that? Just in case that seems to happen. Today's shortcut, so that was a review of the power rule or showing you some other places that you could use the power rule that maybe you didn't think you could. So that's power rule, that's one of them. Product rule is another shortcut. Okay. Remember, I kind of consider there being 4 main shortcuts, so we're on to our second one. On its own, the product rule is not overly powerful. It's still pretty good. It saves you some time. But when I start pairing it with other rules, that's when it really starts showing some of its ability. Some people don't like the notation that you see here. It's basically saying if I take the derivative of one function times another, right? That's what it's saying. It is equal to, well, what does that mean? Just, well, write down f of x. What does that mean? Take the derivative of g. And what am I going to do with the two? I'm going to multiply them together, and then it says plus. So look at this. Another time where multiplication and addition go together. This is amazing. It's like no matter what you do, they're paired together. Right? And then write the other one down, g of x, and take it times the derivative of the first one. Some people like to write it this way. I'm not sure what letter I want to put here, but we'll just do that. Of u times v is u v prime plus v u prime. So it's really the same rule, just shortened up, right? And seeing it's plus, does it really matter what order I do it in? I just know I take one of them times the derivative of the other and then flip-flop it when I do the next part, right? So that's the nice thing about the product rule, is that you can kind of, same thing with multiplication though, it is commutative. Well, let's try this. So do you want to go with the f of x, g of x notation or the u and v notation? Which way is going to work for you? Nobody really has a preference? Well, let's just say then that this one's f of x and this one's g of x, but again, it doesn't really matter. Because let's face it, could I just multiply that out and do the power rule? I could just FOIL this and do power rule on this problem, right? That's why a lot of times product rule by itself, not exactly. Oh, I don't know why I did it in that order. That was weird. All right. So it says to write down the first one. Okay. And then what's next? Derivative of, a lot of times we would call it the second one, right? What is the derivative of g of x? Yes. 4. Yep. Derivative's 4. Now what should I write? Plus. So now we have to take and write down g of x, which is 5 plus 4x, and take it times the derivative of what we would say the first one, which is right here. And what is the derivative of that? Using the power rule is 3 minus 4x. Agreed? Okay. So now all we got to do is clean it up. Now remember, doing this by definition, you'd be substituting x plus delta x in for all those and all that fun stuff. Because some of you are saying this isn't a shortcut. Yeah, it is. So here we go. That's what, 12x minus 8x squared. Or again, when paired with another shortcut, it is. And here we go, plus 15 minus 20x plus 12x minus 16x squared. Well, I spaced that out fairly well, actually, at that time. Am I going too fast, or is it good? All right. Looks like we got some x squared terms here and here. What was that, negative 24? And x terms. So what is that, 4x? Plus 15. And again, keep in mind that that is the derivative, and so that represents a function that I can select x values that are in the original, and it would tell me the slope of that tangent line at that x value. Any x value that's actually in the original. Wow. So we went from that limit as delta x goes to 0 to these shortcuts, but you got to keep in mind of what's really still happening, what that still represents. Okay. Questions? So what's been happening over the years, at least since I've been teaching, is they're trying to get more general with things to see if you can truly understand these rules. Because they find that students, once shown how to do it, students at this level are really good at reproducing that. They can keep doing it. Okay, but so they try and make it much more general, something like this. So suppose u and v are some functions that you notice. Do I tell you what u and v are at any particular time here? Do I tell you the entire function? Nope, because that's basically what we were doing on the front. I gave you the functions, put them in and go, right? Of x that are differentiable, what's that mean again? I can take the derivative there, right? Is differentiable at x equals 3. I know that u of 3 is 2, so what does that mean? Let's translate this. What does that really mean? If I put 3 into function u, I would get 2. So that's a point, or is that a slope? That's a point, right? 3 comma 2 is a point on u. That's really actually the only point that I know on u. What's this saying then? This next spot. The slope at an x value of 3 on u is -1, right? Here is what saying what? One of the points, or is it the slope? The one I just circled in green. It's a point. So 3 comma 6 is a point on function v. That's all I know, though. And the slope at an x value of 3 on function v is 4. That's all I know. So we really hope that they ask me to find the derivative at an x value of 3, because if they ask me somewhere else, I don't know anything about anywhere else. Do I even know these functions are differentiable anywhere else? Well, this might be the only place in the world that these functions are differentiable, but we know it is there. Okay? So now it's saying find the derivative of x times v. So I have to find the derivative of two functions multiplied together that I've never seen, but at an x value of 3. No, we do not have to make the functions because we know the rule. We know the rule that if you have u times v, it's u times v prime plus v times u prime, right? That is the product rule for derivatives. That's what you're told to do. So now I'm told to find this derivative at an x value of 3. Luckily, they've told me everything I need to know at an x value of 3. This one right here is really asking, well, what's u of 3? Well, what is u of 3? It happens to be 2. So this answer here is 2. V prime of 3 is asking for the slope of that one at 3, which is 4 plus v of 3 is 6, and u prime of 3 is -1. So what do we got here? 8 minus 6 is, whoa, that got kind of weird. It looks cool until it hit the equal sign. No, that wasn't as cool as the first one. Yeah, it kind of looks, I don't know, it's a 2 though. So what does that represent? Okay, I was told that that's the derivative of the function of uv. Close. That is if I put 3 into the derivative I don't know. Of the functions I don't know, when multiplied together, I get 2. So I know the slope at point x value of 3 of at u times v would be 2. Have I seen u? Nope. Have I seen v? No. Have I seen u times v? No. But I know the slope if you ever showed it to me. I know the slope would be 2. Okay? But you see how this is much more general. They're trying to see if you actually understand the concepts instead of situating it. How about this one? So same situation. Do we need the product rule this time? No, you could use it if you wanted to, but you don't have to. So let's just do the general derivative. Well, 3 times u. Well, what is the derivative of 3 times u? Well, again, u is some function. Do I know what that function is right now? No. Okay, so it's some big function. It's out there. So it'd be 3 times whatever the derivative of u is, correct? Would have to be? I don't know what it is, though. But u prime is some big function. Like maybe it's this long. Right? Well, yeah, we know that much. But I don't need that. Plus 2 times the derivative of v. Well, what is the derivative of v? V prime. I don't know. I don't know what the function is. Again, v maybe is this long. Or maybe it's that long. I don't know. I don't even know what the function looks like. But I do know if I take its derivative, it's v prime. So now, seeing I'm asking you at 3, we can actually do these as well. So it's 3 times u prime of 3. What is u prime of 3? -1. Plus 2 times v prime of 3, which is 4. So it's what? -3 plus 8 is 5. Since again, never even seeing function u or v, or their derivatives, I could tell you, with the very limited information that we have, that the derivative of an x value of 3 of 3u plus 2v is 5. Impressive. Yes? Mm-hmm. Yep. Because to take the derivative of two things multiplied together, you have to use the product rule. That's what we have the product rule for. It tells us how to take, because product means the multiplication, right? Where here, we really could have used product rule here as well. Ooh, wrong way. So I can just show you quick. We could have used product rule, like say just on this one. It would have been write down the first one. We would call that as like f of x, and then u is g of x. Right, you with me on that? Normally we don't do it for these. So you would write down 3, which is f of x, times the derivative of this one, plus leave that one times the derivative of 3, which is 0. You see how the second half of product rule just goes away? So could we have done it with product rule on both of them? Yeah, we could have. But normally we avoid that. We just kind of use the power rule to the best of our ability on that one. Yep. Yep. Do you understand why it's v and u is not just kind of like, a lot of people think the answer to this one is just 3 plus 2 just by, because you just take the derivative, but it's, you have to take the derivative of that function that you've never seen. I don't know what it is. Yeah, okay, it's not a variable, it's a function. There's a difference. Okay. Questions on product rule?